welcome back. We're talking about vectors in the plane right now, 6.3 day 1. Okay, big long objective, I'm not going to bother reading to you because you're all literate, but here we go. Okay, vectors are very important in physics, a lot of science in general, but physics especially. Okay, they are directed line segments that have a magnitude and direction. Hopefully you just thought in your head, oh yeah, because there's something you may have seen before in a movie. Okay, but anyway, directed line segments that have magnitude and direction. Okay, so if I have my initial point P and my terminal point Q, then I call that the vector PQ. Notice that it's starting at P and heading toward Q, and that's what the little arrowhead right there is going to indicate for us. The little notation, again, very similar to a kind of a ray symbol almost. You have this little kind of arrowhead looking thing on there, and then PQ is just a vector in the plane. Alright, so of course we're talking about planes, so we're sticking to a two-dimensional environment. It is possible to take vectors into 3 dimensions, and we will do that later. But for now, we're sticking to a 2D environment to get used to vectors. So there we are. We're ready to start. Real quickly, vectors are also denoted using lowercase bold letters. So when you write vector PQ, we could just as easily write a bold V to do that. Now, admittedly, it's hard to do on your handwriting, so we'll just be flexible as far as that goes. But the vector right here again, PQ, we could have used what we just did in the last slide, or we could just use a V to indicate that as well. So again, just two interchangeable notations. We'll use both. Just whenever one sounds better than the other, we'll use it. There's the assignment. Again, the 1 to 51 is kind of enough sort of point of view, but there we go. Alrighty, now one thing that you kind of keep in the back of your head, it's not critically important, but the equality of vectors. Alright, so two vectors are equal if and only if they have the same magnitude and direction. Okay, so right now if we can take a look at V being an original vector here, I've got 3 other vectors, and some are maybe equal and some aren't. Okay, at a glance you might think U is equal because it looks pretty much identical, but notice that it starts in the bottom right and goes to the upper left. Again, notice the arrowhead as opposed to this guy. This vector V takes me down to the right, where U takes me up and to the left, so they don't have the same direction. So basically this guy right here is not equal. Oh, that's thick. Alright. Then if we kind of just go around through the quadrants here, we look at T. Okay, well, again, V sends me down 3 and then right 3. Well, if we look at T, we can count 1, 2, 3 down and 1, 2, 3 to the right. So T is actually equal because it does exactly the same thing. It sends me down 3 and then right 3. Okay, and again, the vectors are simply about direction and how far. Distance and magnitude is not about location. So these two are equal even though they're at completely different places on the graph. Thirdly, we've got W. Okay, so again, I'm going down and to the right, looks pretty good, but since V goes down 3 and right 3, W, if we count carefully, goes down 4 and right 4, so this guy also is not equal, and it fails on magnitude. Alright, so yeah, kind of a little picky point maybe, but there it is. Alright, now something that we're going to be using a lot is the component form of the vector. So vector V is going to be basically subtracting the x coordinates and subtracting the y coordinates, but it's very important that the x1 and y1 are the initial and x2 and y2 is the terminal. So we're doing terminal minus initial as we do this. And then that vector V can be denoted as just a solid V1, V2. So basically what we're saying is x2 minus x1 gives me V1, and then y2 minus y1 gives me V2. Kind of the x and the y components of V, if you will. Okay, so before I give you the magnitude, let's go and take a look at this. So V, and again, I can't do bold unless I just do this a million times, and that gets really fast. So we're going to just kind of understand that we're talking about vectors here. Anyway, V equals, okay, so again, the arrowhead down here tells me this is the terminal point, and 3, 4, here's the initial, the negative 1, 2 is the terminal. So vector V, I'm using this fancy kind of V-shaped brackets, if you will. Alright, so again, I'm doing terminal minus initial, so this is going to be negative 1 minus 3, comma, and then 2 minus 4. Okay, and it may seem silly that it's really critical about the order, but if we kind of take a look at how this guy actually plays out, we go to negative 4, and then a negative 2. Okay, now graphically, what's happening from going from this point here over to this point as our vector takes us, isn't that pretty? Okay, well, if we kind of take a look at what's going on right there as we do that, okay, notice in the x direction, going from here to here, I'm going back negative 4 units. So again, from the initial to terminal, I'm going to the left, so that's why it's a negative. Likewise, as I'm going to the other point and going down 2. So it's kind of a slope sort of thing as we're doing this, but again, notice from initial to terminal I'm going left 4 and down 2. That's why I've got a -4 and -2 as my component form of my vector. So basically my component form, vector v equals -4, -2 in those fancy vector notation brackets. Okay, and then the magnitude is going to be denoted by this kind of double absolute value looking symbol. Again, this magnitude just means how long it is. And well, if you notice what I've done right here, I've kind of drawn myself a right triangle, and the length of the vector is going to be this red part right here. Well, doesn't that look like a right triangle? And therefore the Pythagorean theorem would work. Well, obviously that's what it is. So we can fancy this up any way we like, but basically what's going on is this is the v1 squared plus v2 squared. Square root the whole thing. So really, again, just the Pythagorean theorem to get you the magnitude. Alright, so calculating that for this particular example, my magnitude for v, again, once I have the component form, really easy, really fast, -4 squared plus -2 squared, is that 16, achieve a little bit there, that's going to be 16, that's going to be 4, so that's square root of 20, and of course I'm going to want you to simplify that to 2 root of 5. So my magnitude of v is 2 root of 5, and again, that's just simply saying how long it is. Okay, we can go about sketching vectors as well, and I'm using a term resultant. In physics, it probably makes a lot of sense, resultant, but if not, okay, if you look at the word, it sounds like a result, and that's exactly what it is. So if I do certain things with these vectors, whatever it happens to be, the result is kind of what I end up with. But let me show you an example or two, hopefully it makes a little more sense once I've done that. Okay, so I want to do u minus v, and basically here I'm given what u and v both look like. There's no scale on these necessarily, and I am just sketching them, so I'm not going to be super accurate about this, but if I had to impose a scale on this, u looks like it goes about left 1 up 5-ish, and then v looks like it goes right 2 and down 1, again, kind of an ish sort of thing. So if I'm going to do u minus v, okay, basically we'll start at the origin, and then u is my first one, so that's what I'll do first. So u, again, takes me about left 1 up 5, again, ish. So left 1 up 5-ish, something like that sounds like what u is doing for me. Oh, that's crooked. Okay, well, pretend I drew that straight. Okay, and then I'm going to subtract v. Well, v normally goes right 2 and then down 1-ish. So if I'm going to be subtracting that, it means I'm going in the opposite direction. So instead of right 2 down 1, I should be going left 2 up 1. So from here, I want to go, again, approximating left 2 up 1 to get to about right here. And going from there to there, that's about what minus v would look like. And let's change colors here for the resultant. So again, the resultant is where I got ultimately. So I started at the origin, and after doing some terms, what I really did is I went right to there. So then that blue vector right there is my r for resultant. Okay, so that's how you can sketch it, and kind of shows the location to it. Let's do one that's a little fancier. Okay, starting with the same u and v, I'm going to do 2v plus u. Okay, so again, v takes me right 2 down 1. So if I want to do 2v, I can do this one of two ways. And kind of just double each of those as I go, or get out twice. So I'll go right 2 and down 1, and kind of an ish sort of thing. So there's v right there. And then if I go right 2 and down 1 again, I should have something like that. So either vv or, if you wanted to, you could have called that 2v instead. But whatever sounds better to you. Okay, and then I want to add u on the end of what I've done so far. So again, u is going to send me back 1 and up 5. So from here, if I go back 1 and up 5, again, ballparking it, sounds like about right there. So I should end up more or less like that. Okay, so then again, I'm drawing my resultant. It just means, hey, I started here, and made my way over to there. So there's my resultant vector again. Call that r. Make this lobby as quickly as possible. Doing vector operations, not too much of a challenge, but it looks fancy, so it makes me a little bit weird at first. But hopefully it comes pretty naturally in a little bit. Okay, there are some rules on 449 and 451, but the if I gave you these two vectors, u and v, and asked you to do u plus v, and didn't give you any other direction besides that, well, for u, you've got 4 comma negative 2, and if I want to add onto that the vector 5, 1, well, I'm guessing what most people would do, without any other guidance, would probably go, oh, let's just add the 4 on the 5, and that will give me a 9, and then add the negative 2 on the 1, and that will give me a negative 1, and you would be exactly right by doing that. Okay, so I mean, doing that with other things, such as a multiplication sort of scenario here, we've got 3 times the vector 4 comma negative 2, and I want to subtract from that 4 times the vector v, which is 5, 1. Okay, again, it's kind of like these things are parentheses. And so you can distribute into here. So this is actually going to be 12 comma negative 6. And then again, depending on your point of view, you can either distribute the negative 4 or distribute the 4 with leaving the negative out front. I'm a fan of distributing the negative along with the 4, so I'm going to change this to a plus, negative 20, negative 4. And then again, just in the last one, if we're adding together, 12 plus negative 20 is going to give me a negative 8. And then negative 6 plus negative 4 gives me a negative 10. So, again, maybe without much guidance, maybe you would have done that anyway. If not, there it is. And in the book, occasionally we use standard unit vectors. Okay, the I and j. The vector I, please don't confuse this with an imaginary number. This has nothing to do with that. The imaginary number is definitely not a vector, although we will use them in conjunction later. But anyway, here we go. The vector I is basically 1, 0, so it's basically just going 1 to the right. And then the vector j is going to be 0, 1, so it's just going up 1. Alright, so basically, if I tell you the vector u is 2i minus 7j, it's equivalent to saying that u using the other notation that we've been using so far. Okay, notice this is a positive 2 on the I, so that's really just a positive 2 in the x direction. And then the minus 7j, again, j is in the y direction, so it's just having 2, negative 7. Okay, so again, those two are just simply interchangeable depending on what you're looking at any given time. You can use one or the other. They mean exactly the same thing. Alright, all that being said, if you're given two vectors, u being 2i minus 7j and v being 4i plus 1j, and you want to do 5u plus 2v, maybe this is a little bit nicer as far as using your regular order of operations kind of stuff. This 5u is 5 times 2i minus 7j. Again, let's put another hook on the I just so I confuse it with a 1 if I get sloppy. Plus 2 times v, this will be 4i plus 1j. And then from there, it's a little bit more normal, I suppose, as far as doing distribution, combining like terms kind of stuff. So 8i plus 2j, combining like terms, we have a 10i and 8i, gives me 18i. Negative 35 or positive 2 gives me negative 33j. And it's kind of one of those things, since I started with the ij notation, I'll stop with the ij notation. If I had started with the other notation, then of course if I went in this order, then between negative 33 with fancy brackets. But again, since I started with the ij's, I'll stop with the i's and j's. Alright, so one problem I encounter is that I need to make a unit vector in a particular direction. Now, the reason this might be important is I don't want to send a force or some other thing representing the vector in a particular direction, but I want to control the length that it is. So by creating a unit vector, I can control the magnitude, if you will, of the vector, and then I can modify it later as the next example is going to do for us. But for now, let's get a unit vector, which, as it shows here, means on the magnitude 1. So basically what we're going to do is just simply find the magnitude, and then multiply the vector by the reciprocal of that magnitude. Okay, and here it is. Okay, well, again, I've got vector u being 5, negative 3, so now we're going to first thing I want the magnitude of u, which we're going to just simply basically do a Pythagorean thing to it. So I'm going to get 5 squared plus negative 3 squared. And again, please don't square a negative and get a negative. That hurts my feelings. Alright, so again, the 5 squared is going to be a 25, and then the 3 squared is going to be a 9. So the magnitude of u is actually root 34. Okay, so now to get the appropriate unit vector, what I want to do is simply take 1 over that, again, the reciprocal, and don't worry about rationalizing this, times the vector, which is 5 negative 3, 5 1. Right? So basically, this was step 1, this is step 2, according to the list over there, right? So now as I distribute through the vector, I get 5 over root 34 as the first half of my vector, and then negative 3 over root 34 as the second. that a second ago, but just in case. Okay, we're not going to bother rationalizing that. That's how you get a cheer. If you're a hardcore rationalizer and want to rationalize that, I will accept it in a rationalized form. But for now, we're just going to take a break from doing that. Okay, and now as I said in the last example, let's say I want a vector v, and I want it to have a magnitude of 6, but I want to send it off in a particular direction. So, for instance, I want a force of 6 newtons attached to a vector, and here's the direction I want it to go in, so I have to make those two things get together. And so then here basically what we're going to do, find the magnitude again. Well, the magnitude of u is going to be again Pythagorean sort of thing. And trust, okay, a lot of folks probably do this in their head already, but if I got 1 squared and 2 squared, it's really 1 plus 4, so that's root 5. Alrighty. And then, so now, what I want to really do is, again, if I multiply by 1 over root 5, so again, step 1, step 2 kind of thing. Alright, I've got negative 1 comma 2 as my vector. So if I multiply by 1 over root 5, again, I've got a unit vector. So then basically I take that unit vector and then multiply the whole thing by 6. So that's what I'm saying here, the desired magnitude over the vector's magnitude, and then basically do the whole thing all at once. And for space concern, I'm going to kind of slide down to the right as I do this. But 6 over root 5, again, I'm not going to bother rationalizing things. So this gives me a nice negative 6 over root 5. And then I'm going to get a positive 12 over root 5. And again, if you're even a little bit hesitant about accepting that that's got a magnitude of 6, I encourage you to do the Pythagorean theorem on these two values and see what you get. But there it is. That's how you can get a particular direction and a particular magnitude based on a vector. Alright, now let's suppose that I want to write a vector v using I and j with an initial point of 7, negative 1, and a terminal point of negative 0. Okay, now I can either do this more algebraically or geometrically, but here it is. Okay, yeah, I'm not going to bother putting a bunch of tick marks on this because I don't think I need a really great drawing here, but if my initial point is 7, negative 1, it's going to be kind of something like that-ish sort of thing. And I'll even label it for the sake of clarity. And then if I got negative 2, 0, that puts me about right there. 2, 0. Okay, so again, I want my vector goes from one to the other. Alright, so again, I can just kind of sketch in something, hopefully fairly straight. There you go, so there's my vector. Again, I want to call that guy vector v. Okay, but realistically, if I want to use my i's and j's, to my mind, again, I and j just simply means the horizontal versus vertical components. Well, again, I can do some fancy math, but if you look in the x direction, I went from 7 over to negative 2. So basically what that means is I went negative 9 in the horizontal direction. So basically 9 left. And then in the vertical direction, I went from a negative 1 up to a 0. So basically, again, end up positive 1. Okay, so the regular component form would look something like that, but if I'm with the I and j form, again, what that equates to is that v equals negative 9i plus, again, 1j. I won't bother writing it. That's how you can write the vector v that way. Of course, you could use that formula we used earlier doing negative 2 minus 7, which would also give us a negative 9, and then 0 minus negative 1 gives us the positive 1. But at least in this case, I think that's a nice way of going about it, just kind of in a geometric sense. Okay, this is our last example. Those of you that pretty notes, that's pretty obvious. But anyway, there it is. Hopefully it makes a little bit of sense, but of course, as usual, if you have any questions, please ask me in class.